Hello. Today we'll continue talking about embedded surfaces and the curvature tensor. So we're in the middle of a very exciting stretch where we're no longer developing the technique of tensor calculus, but really applying it to differential geometry. This is really a course in differential geometry where tensor calculus is introduced because it just happens to be one of the best tools for talking about concepts in differential geometry. So at the center of our attention, the curvature tensor. So we've introduced it in an extrinsic sense. It very much depends on the embedding of the surface in the ambient space. We've actually not yet introduced a coordinate system in the ambient space. That's not necessary for the things we've talked about so far, and maybe even for the things that we'll talk about today. But we'll certainly introduce a coordinate system in the ambient space very soon. So today we'll continue talking about the curvature tensor, and we'll calculate it for the sphere. But we also have to develop a little bit more of the tensor calculus on surfaces. We've introduced the covariant derivative, but we haven't yet derived a formula for applying the covariant derivative to the normal vector and to the curvature tensor. So today we'll say a few words about those things. That's the focus of our lecture today. I also wanted to point out to you this magnificent sculpture by a Philadelphia artist, really my favorite contemporary artist. His name is Gary Zayon. His name is on the board. You can certainly Google that name and you'll see a lot of other beautiful works of art that he's created. So this one's mine. And it's very much representative of embedded surfaces. So we have an embedded surface in the ambient space. And the sculpture also shows the perfect use for coordinate systems. So this coordinate, so it looks like we've chosen Cartesian coordinate system in the ambient space. And it's a very good coordinate system because it makes the sculpture look most elegant. So that's a good example of appropriate choice of coordinate systems. The coordinate system should always be picked at the last moment in a way that suits the problem you're working on best. So here's a beautiful example of it. So I'll let you admire the sculpture for the duration of today's lecture. I'll just keep it in this corner and maybe move it slightly out of the way when we need to claim a little bit more of blackboard space. So let's very quickly review the objects that we have so far. So we're considering an embedded surface S, a position vector that tracks the points on the surface. The surface is referred to surface coordinates S alpha, arbitrary coordinates. Differentiating the position vector expressed as a function of the coordinates with respect to the coordinates produces the covariant basis S alpha. You pairwise dot the elements of the basis and you get the metric tensor, obviously the central object. It's S alpha dotted with S beta. That's the covariant metric tensor. The contravariant metric tensor is the matrix inverse of the covariant metric tensor. And of course, the contravariant basis is the covariant basis with the index raised. Okay. Having the basis immediately gives rise to the Christoffel symbol, which we had to use this formula for its definition. You can review the last lecture to find out exactly, to be reminded why it's this formula and not the other one that needs to be used as the definition for the Christoffel symbol. And once we have the Christoffel symbol, we have immediately our covariant surface derivative nabla alpha. Okay? So we've immediately learned of the metronylic property of the covariant basis of this derivative with respect to, so covariant basis is the one exception. But with respect to the two metric tensors, this derivative applied to either one of the metric tensors produces 0, a set of 8 zeros, as if the surface is two-dimensional. So what else do we have for free by direct analogy with the covariant, with the ambient space, with the Euclidean space? Well, we also have the symbol S, which is the determinant of the covariant metric tensor. And of course, its square root is called the volume element, or maybe more appropriately, the area element. And once we have that, we have the Levi-Civita symbols, because we can similarly define the permutation symbols, whereas in the ambient space they were EIJK. Because we're in two dimensions now, it has to be EIJ, and maybe EIJ with lower indices. Use Greek letters, of course. So EIJK in the ambient space, E alpha beta on the surface. E alpha beta, E alpha beta. Those are defined as 1s, -1s, and 0s. And when this is this one is divided by the volume, the area element, and this one is multiplied by the area element, we end up with tensors called the Levi-Civita symbols, or maybe the Levi-Civita tensors, denoted by the letter epsilon, epsilon alpha beta, and epsilon alpha beta. So all of this works by complete analogy with Euclidean spaces. And it's also easy to show that the covariant surface derivative is metronylic with respect to the Levi-Civita symbols. So this operator right here kills this element, this element, this element, and this element. However, quite logically, it does not kill the basis elements. And the reason for that was curvature. And that observation actually gave rise to the curvature tensor. It was defined in the following way. The derivative of a basis element was found to be proportional to the normal, and the coefficients of proportionality were called B alpha beta. Of course, the index can be raised on both sides, and the reason for that is the metronylic property of the covariant derivative with respect to this object, because if you take this identity, you can multiply both sides by the contravariant metric tensor and contract, and due to the metronylic property combined with the product rule, the contravariant metric tensor can come inside the derivative operator and raise the index on S. Okay. So that's curvature tensor with the index raised and contracted. The alpha is mean curvature. We'll talk a whole lot more about that object. Okay, so here's where we're at. Here's what we need to figure out. In order for this to be, it's called tensor calculus for a reason. In order for a certain technique to be called a calculus, there needs to be a rule for differentiating every single object of importance. So the objects of importance are the covariant basis, the normal, perhaps the curvature tensor, and so forth. We basically need to have a derivative for every important object. We already have the derivatives for these four objects. They're 0. For this object, that produces curvature. The next interesting question, which we're about to answer, is the covariant derivative applied to the normal vector. So let's figure that out first, and I think I have just about enough space on this board to figure it out. And notice one interesting thing. We still don't have an explicit relationship for the normal. we don't have normal equals. We soon will. In order to have that formula, we will need to introduce a coordinate system in the ambient space. But that's actually not necessary in order to figure out the derivative of the covariant derivative applied to this normal. After all, this normal is given by the fact that it's unit length and by the fact that it's orthogonal to each of the basis elements. That's the definition. It needs to be orthogonal to the to the tangent space, which means that it's orthogonal to each element of the basis, that spans the tangent space. So let's choose S alpha. Because these two relationships define the normal, they should be sufficient to figuring out the derivative of the normal, the covariant derivative of the normal. Okay, I also want to mention that when I say define, normal is a little quirky because it actually defines it up to a sign. We can choose an exterior normal, we can choose an interior normal. This would be the exterior normal, the interior normal would point in the So the terms exterior and interior, of course, can only apply to a closed surface. If the surface is not closed, if it's just a patch, a two-dimensional patch in three-dimensional space, then you can't call those two normals external and internal. You can just realize that there are two normals. And of course, if you replace the normal with the one facing in the opposite direction, this would still hold, because these would both pick up a minus sign, and so one would remain. And of course, this would still hold, because equaling 0 does not depend on whether you choose the normal pointing in one direction or the other. So of course, the normal is defined up to a sign. So these nearly define it up to a sign. A very interesting singularity. So this point has important implications for the curvature tensor. Because you see, there's a normal that figures here. And if this expression doesn't specify which normal you take, so there's no normal dependency on the left-hand side, but the right-hand side seems to depend on the normal, and it kind of does. So depending on which normal you choose, these coefficients might change sign. So if you choose one normal, you'll have one set of coefficients, 4 coefficients. But if you choose the opposite normal, then the coefficients of proportionality would have to change their sign. That means that the curvature tensor, and therefore mean curvature, depend on your choice of normal. So it would be more precise to say the curvature tensor of this surface with respect to this choice of normal equals whatever it is. So when you specify the values of the curvature tensor, you have to choose a normal. And that's an interesting thing to pay attention to throughout for all expressions that involve the curvature tensor, because they should all depend on the choice of normal. So that's one of the things to pay attention to. Things need to be consistent, essentially, on both sides of the equation. So remember, when the normal's flipped, everything about the curvature tensor, all entries of the curvature tensor, change their values. Okay, with that in mind, let's use these two identities to figure out the derivative of the normal with respect to S alpha, the covariant derivative. Okay, so of course we'll do it by differentiating both of these identities covariantly. So when we apply the covariant derivative to this identity, let's think about what will happen. On the right-hand side, of course, we'll have 0. It's something to actually give a little bit of careful thought, because when you apply covariant derivatives to constant tensor fields, you don't necessarily get 0, but this is a tensor of order 0, an invariant, so for invariance it is true. And on the left-hand side, we will use the product rule. So without writing it down, here's what I'll say. I'll say that the derivative of this normal times this normal plus this normal times the derivative of this normal equals 0. And of course, the two terms that I just mentioned are the same by the commutativity of the inner product. So we can combine them. And as a result, we get this identity, that the derivative of the normal is a quantity dotted with the normal is 0. That's one of those super fundamental facts of life, where if you have any sort of vector, depending on any sort of parameter, changing in time while keeping its length, its rate of change will always be orthogonal to the vector itself. So if you have a vector moving through space, changing in its orientation but not its size, then the velocity of the tip, probably minus the velocity of the other tip, is orthogonal to the vector itself. That's equivalent to the vector keeping its length as a function of that parameter. Okay, so you can think of it as this being the normal component of this object. This is the object we want to calculate. This is not enough because it only gives us the normal component, and it tells us that the normal component of this quantity is 0. That's not surprising. So this derivative lies in the tangent space. That's a very nice discovery. And because it lies in the tangent space, it must be some kind of linear combination of these vectors. So let's discover what those coefficients are. So it will be some object with two indices, right? Because each one of these vectors needs to be decomposed with respect to the covariant basis. So wouldn't it be nice if it's the curvature tensor, right? Because how many other objects do we know on the surface with two indices? The metric tensor, of course, but also the curvature tensor. So it will actually end up being the curvature tensor, which is quite a nice revelation that the derivative of the basis gives us the normal and the curvature tensor. The derivative of the normal will produce the curvature tensor in linear combination with these vectors. So you're about to see it. So let's apply the covariant derivative to this object, to this identity. Let me see where we should start. Here's what we're going to do. I will erase the 0 and write it on the left-hand side. And I will apply the covariant derivative, alpha is taken up, so it needs to be beta, to this object. All right. So I'll go through it slowly so you can maybe do it along. You don't really have, things are so short and simple, you don't really need to write it down. You can just almost do it in your head. So here's what's going to happen. We're about to use the product rule. And here we'll get the object we're interested in, the derivative of the normal, dotted with the vector, with the basis vector, plus the normal dotted with the derivative of the basis vector, which will of course produce curvature tensor. And it shouldn't be then too hard to identify this object. All right, so here's what happens. We get the derivative of the normal, and this is an object, quantity, dotted with S alpha, plus the normal, dotted with the covariant derivative of S alpha. Okay. Let's see what happens here. So we recognize what this object is. This object is the normal times B alpha beta. It looks like B beta alpha, but as we discussed, it's symmetric. I don't think I've actually ever shown it, but I will fill that gap at some point. So this will be the normal dotted with the normal times B alpha beta. Of course, the normal dotted with the normal is just 1, so this is B alpha beta. And this is what it is. So let's actually bring B alpha beta to the left-hand side. So we have this expression. Excuse me. Dotted with S alpha equals minus B alpha beta. And now this is dry enough to put the normal back in. So, very interesting minus sign. So you will find it throughout differential relationships on the in differential geometry. So we saw it when we were deriving the Christoffel symbol. We see that minus that appears in the differentiation of covariant tensors, and of course it's basically the same minus that comes from the product rule, lending one of its terms to the right-hand side. Okay, and from here, it actually follows, I'll leave it to you as an exercise, but what you should do, excuse me. Yes, so I'll leave it an exercise. From here, it's very easy to show that this object well, I think I should show it. So, okay, so I'll pause right here, I'll erase this part of the board, and then I will actually derive what this object equals in terms of this and this. Let's derive this object. So, here is a good way to do it. I think with experience, the combination of this identity and this identity would be sufficient to just basically eyeball the fact that these represent the coefficients of this object with respect to the basis. But let's be a little bit more systematic about it. So okay, so I'll just choose indices and then I'll rename as I want, and then I'll rename them as I have to. So let's take a look at this vector. So you can say it's a pair of vectors for each value of alpha, but it's easier to call it a vector even though it's a pair of vectors, because you think for each value of alpha, 1 or 2, it's a vector whose coefficients, whose components we're trying to determine. So, okay, but then of course, we're talking about two vectors at the same time. So you can say these vectors, or you can say this vector, realizing that you're having the same discussion twice. Two alternative but equivalent way of thinking about it. So this is some kind of vector in space. We kind of already know that it's orthogonal to the normal vector, but let's pretend for a moment we don't even have that insight. So we'll just say that its components with respect to the normal are, let's think of a couple good letters, x and y. So x times the normal. Okay, so that's the components of this vector in the normal direction, plus in the tangential direction, that's two-dimensional. So we have to have sort of like 2 by 2 set of numbers, 2 numbers for each of the vectors, times s beta. Okay, because these 3 vectors, this one and these 2, form a basis at any point on the surface, but not just a basis, it's a basis for the 3-dimensional space, not just for the tangential space. These 2 take care of the tangent space, and this one takes care of the remaining dimension. Okay, so here's the number one thing you would do to determine x sub alpha. You would dot both sides with the normal. I will have space. I will save space on the. I won't save space. Let me just do it. So dotting both sides with the normal. Maybe it's a little easier for me because I've done it so many times. So this is me dotting the left-hand side with the normal, and then dotting the right-hand side with the normal, plus y alpha beta are unknown coefficients, s beta dotted with n. Of course, this is 0 because the normal is orthogonal to the tangent space. This is 1. I was very careful to just cross out this part. This is 1. And this, of course, is 0 by the identity that we just derived. So as we expected, these coefficients are 0. There is no normal component. Okay. So now, in order to find out these coefficients, I will dot both sides of this identity with respect to s beta. Excuse me, that letter's used up. S gamma, contravariant S gamma, just for convenience. So we'll have S gamma dotted with grad alpha n. Equals x alpha and S, so like I said, I'll take the contravariant one just for convenience. Of course, the indices can move up and down quite freely. That's just index juggling of indices plus y beta alpha S beta dotted with S gamma. All right, let's see what we have here. What we have here is this is 0 for the same reason as this. The normal is orthogonal to the covariant basis. These guys are mutually orthonormal. So this is this is delta gamma beta, Kronecker delta, which will of course rename this beta to gamma. So we'll have y gamma alpha all by itself. Alpha, y big gamma alpha all by itself, which is our goal. Our goal is to determine this quantity, so that's good. So let's see, so y gamma alpha equals S gamma dotted with grad alpha of the normal vector. Okay, and now we can refer to this side where we're looking at the exact same thing with the index lowered and the indices renamed. So we can rename them according to, so that it matches this, and we will get minus b raised gamma alpha. And there you go. The coefficients of this object with respect to the covariant basis are minus the entries of the curvature tensor. So let's write down this, what we just found somewhere so we can box it. So I guess this is as good a space as any. So here's the final entry of our differentiation table, that the covariant derivative applied to the normal vector, of course I'll rename the indices to make this as elegant as possible, equals minus b beta alpha S beta. So a beautiful formula that shows that the derivative of the normal lies in the tangent space and that the coefficients of proportionality are the entries of the curvature tensor. So you can almost say that the derivative of the normal is the curvature tensor. Okay. Does the left-hand side depend on the choice of normal? Remember, there are two normals pointing in opposite directions. Yes, of course it does. It's proportional to it. So the right-hand side had better have like dependence on the choice of normal, and of course it does. So this normal and this curvature tensor must be coordinated. So remember, these values depend on the choice of the normal. So you have to, throughout your analysis, choose them in consistent fashion. All right, so this curvature tensor must be coordinated with this normal. And then if you choose the other normal, this left-hand side will change its sign. But of course, when you choose the other normal, you have to recalculate your curvature tensor. So this object will change its sign. So everything's consistent. And actually, I think that this relationship also deserves to be boxed in a slightly different way. I'm about to rename a couple of indices and move the minus sign to the right-hand side. And then you can think of it as another explicit relationship for the curvature tensor. Equals minus the derivative of the normal dotted with a contravariant basis. This is nice because it gives an explicit expression for the normal. Once again, you see that it depends on the choice of normal. So that's very clear and good to see that it's consistent. And number two, this identity is actually more convenient than this identity, which may be written like this equals normal dotted with this. So you obtain this identity from this one by dotting both sides with the normal. Okay, so let's box this as well. These could all be used for the computation of the curvature tensor, but of course I prefer this one. I prefer this one because this is a covariant derivative applied to an invariant. So it just coincides with the partial derivative, and therefore does not require the use of any Christoffel symbols, which makes it, if you're calculating things by hand, especially for a shape as simple as the sphere, kind of makes the calculation a little bit simpler because you just have to evaluate one partial derivative, and that's it. So we will actually use this expression to calculate the curvature tensor of a sphere of radius r. And the last thing I wanted to mention is you can kind of see that I'm not careless, but completely free with placing indices, because the indices can be juggled freely. And it's especially important to realize that it's the metronylic property of the covariant derivative that allows us to juggle indices freely, because these objects appear under the covariant derivative. So if the covariant derivative didn't kill the metric tensor, you wouldn't be able to raise indices on both sides of this identity. So, but I'm almost insensitive, and you should be also, to the placement of indices. They can just jump around and be juggled any which way you want. And with things like the metric tensor and the curvature tensor, you don't have to particularly pay attention to which index is first and which index is second, which makes it particularly appealing to write the curvature tensor with one upper and one lower index, because it's symmetric. If it weren't symmetric, we would have to really give each index its own slot, and when we juggle them, we have to make sure to keep track of which index is first, which index is second, or else you can very easily make a mistake and obtain the wrong result. Okay, so great. This is a very good looking board. And unfortunately, I have to erase it, and we'll then use this expression, that's our next order of business, to calculate the curvature tensor of the sphere of radius r. And then, of course, we'll continue talking about curvature for a very, very long time. Okay?